Okay, I think we can start now. I would like to welcome all of you at this session. I hope it's going to be very interesting session on scheduling applications on the grid. And as you might have seen from the program, this session will be devoted to several scenarios that we made available or people made available for the grid using different tools and methodologies. So my name is Nabrzyski. I'm from PSNC, and I have a pleasure to chair this session. Actually, all of the presentations will be the PSNC's presentation. So this is kind of a PSNC's presentation session. But I think you're going to find it interesting. So the first presentation is going to be presented by Krzysztof Kurowski from the Applications Department of PSNC. He's going to talk about the grid authorization service that was developed under the GridLab project.
Okay, can you hear me from the back? I think so. Okay, so thanks, Jarek, for your introduction. My name is again Krzysztof Kurowski, and I represent Poznan Supercomputing and Networking Center. And before I start, I have a quick announcement, because we are responsible for this conference, and lots of technical people, including me, are involved in many different things around this conference. And so for those of you who still don't know where toilets are, they are on the right-hand side when you get into the building. I had to answer this question 1,000 times yesterday. But anyway, let me start my presentation. So I would like to talk a little bit during my short talk about grid authorization service and the way we integrated this service with other components, and all these components we've created in the scope of the GridLab project. So here's the short outline of my presentation. So first of all, I would like to describe a little bit the GridLab middleware architecture we proposed, and then I would like to present GridLab authorization service, which is called GAS, then talk a little bit about GridLab resource management system, and then also about very useful mobile services we've created in addition to these two components. And finally, I would like to present some new scenarios which are very hard or even impossible to implement without such a grid middleware services. And finally, I would like to conclude my presentation. So yesterday, we had a great chance to listen to Ed Zeidel's talk, and he presented lots of new ideas for network technologies. And one of the main conclusions was that we really need new network technologies, and we really need good bandwidth. We really need a good capacity to transfer more quickly files from different resources, or just to speed up, I don't know, streaming of video or wherever. But at the same time, or on the other hand, people, end users, are not so willing to deal with new technologies. They still would like to use high-level services, and because they want to focus on their applications, and they want to do research, and they don't have time to learn all these new technologies. So the idea behind GridLab was basically to propose a new layer between low-level complex mechanisms and protocols, and build a bunch of useful grid middleware services, which in fact abstract the functionality which is provided by core services. So people can use very nice and user-friendly tools on the other hand, and use operations or use capabilities provided by these high-level services to get access to distributed infrastructures. So, as you can see, we would like to abstract core mechanisms and core technologies and build a set of useful tools. And let me stop here for a minute. And this is the architecture we propose. So as you can see, you can imagine distributed environment, lots of resources connected together via via network, and on the top of these resources, we've deployed in the GridLab lots of core services, mostly taken from Globus, and all these services provide remote APIs. And on the top of these core services, we were able to implement grid middleware services, and all this. So I would like to talk and focus on 3 of them, and all these services provide secure web service interfaces, so they can also exchange messages, and people can easily, on the top of these services, build different clients. So for example, portals, or integrate their applications via these interfaces. So let me start with GAS. We were not so satisfied with authorization mechanisms in Globus. They are very static. So in order to add a new user, you have to modify a GridMap file. Or imagine that you have like 100 of resources, and you have to add a user. Then you have to modify a GridMap file in every place. So we have many new scenarios. So we came up with the idea of having a new authorization service, and it's in fact considered as a trusted single logical point in which we store all security policies. And the architecture of this service is modular, so it allows us basically to add new modules for communication, database support, because we would like to store all security information in a database, service management, and integration with external security solutions. And for those of you who are familiar with some existing authorization services, the basic functionality of GAS you can compare to for instance, CAS from Globus, Acanti, or VOMS, or Permis. So here's the GAS internal design. So at the beginning of the project, we focused on a core functionality. So we implemented RAT and airbag security models, and then we decided to add some useful models, for instance, for gas management. We've added also a new model for storing security policy, and also a new model for communication with external services. And right now we are also working on a SAML and XALTM protocols in order to integrate this service with message level solution. So what are the GAS main features? Because we had really strict requirements towards portability, flexibility, and performance, we've decided to implement from scratch this service in ANSI. And one of the main functions which is provided by GAS is a get authorization decision, and the answer is yes or no. And here you can see also an example RAT policy. So you have different subjects, objects, and operations. You can connect these pieces together in many different ways, and in fact build a hierarchical structure or many different groups and relationships between these groups. And GAS itself is able to generate not only a simple answer, yes or no, but also is able to generate a logical part of security policy. And we, in addition to service, we've created also some really nice end-user tools. Missing issues. So we still have to add some functionalities within core component. We have to spend some time and implement the airbag model, and we have to also improve documentation, and as I said, also add new components in order to integrate GAS with new technologies. And it's open source, so please feel free and go to the website, which is shown on this slide, and grab the stuff and try to use it. Here are some screenshots. So as you can see, you can define a simple policy, but also a hierarchical structure of policies, different policies within GAS. The next really key component we've created in the GridLab is called GRMS. It's a grid resource management system, and because Globus still doesn't provide mechanisms on a higher level, so you have to, in order to satisfy scenarios or requirements, if you have like different resources and many global services, and you have to have some mechanism on the top of these services. You have to have a mechanism for resource management or just job management, because you can imagine that not only one application get access to these resources, but you have many applications, so you have to control somehow all these applications. And basically, GRMS allows you to do that. And also, GRMS is able to contact many different information services, distributed information services. So GRMS itself is able to get information about the infrastructure, so you don't have to check the status of resources or services. You just use high-level APIs of GRMS for job submission or job control. And you can compare GRMS also to some existing grid job management systems like CondorG or CSF from Platform. Here's the GRMS internal design. It's a pretty complex system, believe me. And as you can see, GRMS is able to talk to low-level services, mostly taken from Globus, like Grid FTP, to stage in and stage out files, but also to control remotely jobs, and also is able to talk to Mercury system, which is low-level distributed monitoring system. But in addition to this, GRMS itself is also able to talk to other high-level services, for instance, gas, to get an authorization decision from gas. So it's really useful, and in fact, GRMS and gas, there are two key components within a grid middleware. And as you can see on the top, because GRMS, as all other services does provide GSI-enabled web service interfaces, so you can connect to GRMS from different clients, like command line client, web browser, or even mobile devices. What are the main GRMS features? So right now, there is GRMS 2.0 alpha version available, and we are able to, GRMS is able to do matchmaking. Also, we've introduced new components for job rescheduling and workflow management. And it's portable because it's written in Java, and is able to talk to different services like global services. In addition to this, also Mercury distributed information system, or iGrid. GRMS is able to also talk to notification service. So imagine the scenario in which you can get a SMS after you submit a job to remote site. And also GRMS is able to store all information in database for accounting reasons, so people can see, mostly administrators, what happened in the past. And it's also open source and free. There is a web page, so please visit this web page in order to get more details about the system. Various clients we've created, like a simple command line client, but also a portal access and some nice statistics. The last not least service we've created from scratch is a GridLab mobile service. And this is, in fact, a bridge between mobile devices and grid middleware services. So we had some scenarios in which people were using mobile devices in order to submit or control jobs on remote resources. So we decided to implement like a bridge between grid middleware layer and GSM infrastructure. So you don't have to have laptop connecting to the internet in order to perform some actions on a distributed environment. And in order to get you an impression how it looks like, So there are some screenshots taken from mobile devices. So this is the same architecture I presented before. It's kind of three-dimensional view. As you can see, GRMS. Can I have a point? No, I don't have a pointer. Okay. So imagine that GRMS is able to talk to gas, and GRMS controls all jobs on the remote resources, and people don't use low-level mechanisms like Globus services directly, but they are using user-friendly interfaces in order to perform even complex operations on distributed resources. And all these services, because we do support GSI mechanisms, all these services perform operations on behalf of end users. So we really would like to introduce, and actually we did many scenarios, and we presented many scenarios in which we've shown that the delegation mechanisms are very useful. And the concept itself, I mean, single sign-on, it's really useful. So people don't have to log in and to different services, resources in order to perform operations. Then they just have a proxy certificate, and middleware services in the middle perform some operations on behalf of end users. And recently, we have integrated gas with Globus using call-out mechanisms from Globus. So let me just back to this slide. So as you can see, Globus services get authorization decision from gas. So you don't have to have like a list of users within a GridLab file, but all information about the account and about the user could be taken from gas. And here are some technical details. As I mentioned, we don't need to use GridLab file anymore. We would like to also use a concept of having virtual accounts, so you don't have to create a new account for a new user. Once a new user comes to your infrastructure, you can map a new user to a virtual account which has been created on the resource, and the mapping itself is stored in gas. Okay, so one of the scenario we presented was a cancel scenario. Imagine the scenario in which you have a long-term job, and it's very, very hard for one user to control this kind of experiment. So you would like to delegate some rights to other users. And without modification within Globus, it's impossible, because a user who submitted a job to a resource is responsible for all operations performed on this job. And using, for instance, our services, you are able to delegate rights to another users, so they can control this job on behalf of you. So they can, for instance, cancel or migrate this job or suspend this job, and have full rights to perform such operations. And this is the last, not least, slide. So we would like to promote products we've created, mostly in the scope of the GridLab project, in a new umbrella which is called Grid. So the idea is to have high-level or production-level quality software in order to deploy these services in potential customers. There is a stand during this conference, so please feel free and go visit our stand here during the conference. There are more guys, and they are more than willing to answer all your questions. Many people are interested in services we've created, so we would like to add new capabilities, new functionalities to these services. In new projects, there's a list of projects like HPC Europa, IntelliGrid Progress, or Clusterix. And of course, in new releases, we would like to fix many bugs and have more and more, as I said, productive quality software. So thank you.
Thank you very much, Krzysztof. It was very fast, I must say, so you have plenty of time for questions. Any questions?
No questions.
No questions.
So again, please do not hesitate and visit our stand during this conference, because we would like really to talk to probably lots of you are interested in this kind of solutions we've created for resource management problems and authorization to solve these problems. So please feel free to visit us.
Okay, and thank you very much again. The next speaker is Marcin Okoń, and he's going to present the scheduling interactive jobs on a grid-based systems. I think this will be experiences from the VLab project that we also run on national grid as a national grid project in Poland. So you have like 5 minutes more if you want to use it.
Thank you. I will. All right, I think we can start. Good evening, ladies and gentlemen. My name is Marcin Okoń. I, of course, work for the Poznan Supercomputing and Networking Science. And I'm going to give you a few words about one of our solutions developed in one of our projects. My presentation will be related to the previous one because the solution incorporates some of the things you've just heard. For example, GRMS. So the outline of my presentation is, first of all, I would like to introduce you to the problem we are dealing with, which is the scheduling of interactive tasks in the grid. Then I will tell you a few words about the project for which we have developed this solution. This is a virtual laboratory project. And then I will briefly present to you our proposed solution to this problem, and I welcome any comments and suggestions. Because right now the solution is working and it is proven to be useful, but of course if you have any suggestions, please write it down and you can ask me and discuss these things during the questions or after my presentation. So first of all, the chosen aspects which we have to deal with during scheduling interactive tasks. By interactive, we mean tasks which are performed in real time by the users with the usage of graphical user interface. They are not the batch jobs that we can just run and forget about it, and the computations are done. We just inform that we got the results. So what are those aspects? First of all, this is quite obvious that the user has to be present during the task execution time. So we have to schedule the task in a way that it is synchronized with the user's possibility to be at his computer and to be able to perform computations. Another thing is that in some cases, which we are dealing, particularly in the virtual laboratory project, is that sometimes the user must be present on the other side. By the other side, I mean, for example, a scientific device of any kind that the end user is logged onto. And sometimes that device requires an operator which is available on site and has to do some adjusting or other things. Of course, there's an aspect of resource availability. Of course, this is related with this scientific experiments case. Sometimes the scientific equipment needs to be maintained and turned off for some periods of time and so on. And this also has to be considered. Another thing is, of course, the workload and the resource allocations. That we have quite problems. We have problems with balancing the workload between devices. Of course, there's an issue of interactive connection to the graphical user interface, because we have to provide our users the actual interface which they will use to perform their experiments, because we are assuming that they are connecting via the internet in general, and they do not have to have any special software installed, just the web browser. So we have to provide a mechanism to display them the graphical interface. Another aspect is the dynamic measurement scenario. This is the special thing related with our virtual laboratory, and I will tell you a few words about it in a minute. Okay, so first of all, our project, virtual laboratory. What is it about? Mainly, the virtual laboratory is, as highlighted, about enabling remote access to complex and expensive laboratory equipment. And the tasks we are talking about are just the research experiments which are run on that equipment. Another thing is that the dynamic measurement scenarios are introduced. These are the graphs defining the whole measurement processes. This will be explained in my next slide. There's also a science library, because the virtual laboratory is more about creating complete environment. So we also provided the digital science library, which is able to store our results, to share it, to publish it, to do whatever we want. This is also related with data storage and management, because we are incorporating capable systems for storing and retrieving large amount of data. We also had an educational potential in mind, of course, and we also provide the tools to enable work groups collaboration. Okay, so just a few words about the dynamic measurement scenarios. What are they? They are the graphs, basically, which define the multidimensional processing experiments. We have the diagram describing a sample scenario. As you can see, we have some steps defined there, which the experiment, the second box, defines the actual interactive task, which we are performing on the computation on the experimental machine, on our laboratory equipment. And we define a few steps, such as pre-processing. The data are processed, then they are moved to actually the scientific device to be used as an input data for performing our experiment. After the experiment, we can decide, and this is the dynamic part of the scenario, whether we want to move to the post-processing. If we are not happy with the results, we can schedule another task, which is about the post-process the data, or we can move directly to the visualization and obtain the results. Of course, if we are after post-processing, if we are not happy, we can move back to the beginning of this process and start once again with the pre-processing, but using the data actually post-processed, and we can just input it once more and do some more computations. And this solution is already implemented. This is a screenshot for a sample measurement scenario. As you can see, we have it's a little bit complicated. It consists of 3 actual scientific experiments. 2 of our, one, it's a question mark. It's undefined at the point that the screenshot was taken. We still don't know what we want to perform there, but the 2 others are from the domain of chemistry experiments. Then the arrows connects it to the post-processing task, which is symbolized by this computational machine. And then we have another computational task and visualization model in form of the particle. And that's just how it does look like. So we can, of course, open any of those boxes and define various parameters, defining the tasks, the input and output variables, data, and other aspects. This is, of course, highly customizable, and a user can define exactly the scenario he wants to perform. All right, so to the point. First of all, a quick look at the batch job scheduling we have in the virtual laboratory. It's quite straightforward, because as you can see, the bottom half of the upper half of the picture, we have a VLab environment. And on the bottom half, it's a grid environment. And the main point is that we want to transfer our tasks submitted by the users to the grid side. and to perform them transparently for the users. So we've created a module called Grid Gateway, which is responsible for translating virtual laboratory tasks into the tasks as seen by the grid environment. And for example, as you can see, we implemented a connection with the GRMS systems, which proves to be very useful and basically works. So the jobs are submitted by our scenario management modules that the screenshot was taken a slide before, then are transferred to Grid Gateway, and then transferred to the grid itself, to the management service, and they are scheduled and run. Of course, the data are transferred separately in a separate connection. As you can see, the data management system, there's a part of the VLab project, transfers data to the machine which is selected to run the actual task. But this is the batch job scheduling, and it's quite easy. The main task was to develop a solution for interactive tasks. So we have to distinguish a few steps. First step is to submit an interactive task. So the first step will be, from the VLab portal, task is sent to the special module. We are talking about the virtual laboratory site right now. We are in our system. We have a module called Scenario Management Module, which analyzes the graph and decides which task it's what is the time that the task should be sent to be scheduled to be put into the system. Of course, this module adds the task to the database, registers the tasks with the system via the monitoring module, then sends the task to the scheduler on a global level. The scheduler decides, first of all, do we have a right to submit the task? We are using some kind of grid authorization. For example, it could be the grid authorization service. In the first step, we have to decide, do we have the right to submit the task to the grid in the first place? Then we check the accounting, if we have enough credit to run the task actually. And we submit the task to the GRMS via the Grid Gateway described in the previous slide. So the next step is to schedule a VNC session, because we chose to use the VNC as our main tool for enabling users with graphical interface of the applications. So now we have to schedule such a VNC session. So how is it done? First of all, GRMS checks with the monitoring, for example, monitoring and discovery service, what resources are available. Then, in the second step, verifies in the resource database. It is called VNC session database, but it's more of a general database for keeping resources allocations. Then verifies the free slots for VNC session on a given resource. And of course sends back this information to our system, to our VLab, which is informed via the notification, which is provided by GRMS module. And we update the task status in our portal, and the user is able to see that the VNC session was scheduled at a given specific time. So when the time comes, the task is sent to be run, and now we have established a secure connection using a VNC protocol to enable users with the graphical interface of an application which is about to be run. So the GRMS launches the scheduled task, and it's not the task itself, but it's, as you can see on the diagram, it's like in a form of VNC manager. It's kind of a wrapper which is responsible for running the actual task. So every application enabled in the system has to have such wrapper written, and the wrapper is responsible for launching VNC server in the first place, for launching the actual application with the display routed for the display set to this VNC server, then to create a specific password for this session, VNC session, and to return back this information to the grid gateway so it can be transferred back to our portal. So as you can see, GRMS, after the task is sent to be executed, the GRMS sends the notification to the gateway, and then the VNC manager sends the information about the VNC session password and the port number in which the VNC server is listening. And another thing is, after such information is sent to the portal, the user is able to run the VNC client application and actually to connect to that running task. And of course, the whole process is transparent to the end user. User doesn't know anything about this mechanism. He's given just a simple link in our portal to launch the select application, and the application checks with the monitoring service, obtains a proper VNC server address, port number, password for that user, and opens the connection. Another thing is, of course, the connection it's open for a given amount of time. So the user just requests during the task submission process how much time does he or she need to perform computations. But when this time is about to end, the user is presented with a warning that his time is about to finish, and he's able to request for the session, for prolonging the session. So how is it done? First of all, it's the request itself. It's sent by the user. Then the request is once more verified with the grid authorization, whether the user has or has not the right to prolong the session. Then it's account for checking if the user has enough credit to extend his session. Then the request is forwarded, then of course verified with the session or resource database. And of course, after the database verification, we can determine if we have resources available and we can prolong the session, or we have to deny the grant. So the answer is returned and the user is informed of whether it was a success or denial. So how the session is ended? Of course, the user decides that his or she is done with the computational part in this task, and the task has to be finished before its execution time. So request is sent from the portal to the grid gateway, which informs the GRMS that the task is about to be finished. And of course, GRMS sends the info to the VNC manager to finish this task. And of course, the application is closed. The VNC server is also closed, and there's no way that the connection is still valid after the user decides to end his task. And of course, the resource database, of course, is updated, and the resources are available for another user, for another scheduling sessions, for another applications. And the last step, of course, is to update the task status. Another thing is that sometimes the system has to close the applications because, for example, the time expires, or there can be any other reason. In case of scientific equipment, that may be some kind of malfunction or sudden change in the maintenance periods or whatever. The system chooses on GRMS level. When GRMS time expires, for example, GRMS sends end signal, and it's quite the same as on the previous slide. The procedure is very similar. So GRMS sends a signal to the VNC manager to close the task, to finish the VNC server, and so on. And the resource database is fed. So the status can be updated and task finished. So to sum things up, scheduling of interactive tasks, of course, it's quite interesting because it enables to find new fields of interest for the grid portals for the grid applications. So it creates new possibilities, and especially in the domain of virtual laboratories, in which we are dealing, where there's a lot of graphical processing, data processing. Of course, it's quite interesting and rewarding topic to enable to schedule interactive tasks. Of course, there's one major flaw, which is the human factor, and it's the main non-deterministic element which influences the whole process, because of course we can provide all the mechanism, all the algorithm and everything, but it is the user that actually must be present during the task time execution and to actually perform the computations, to finish the task on time or just prolong the session and finish the computations so we can move to another step in our measurement scenarios. And just to remind the following steps during scheduling of interactive tasks, which are the task submission, then there's the scheduling on VNC session, establishing a secure connection, and the VNC session ending. Of course, you can learn much more about this solution at the PSNC stand in front of the registration desks. We have a small desk when you can learn more about the virtual laboratory, maybe see a presentation, online presentation, how the dynamic scenarios work, how the interactive scheduling actually is implemented into practice. We can schedule an application, run it for you, and you can see simply how it works. So if you have any questions, do not hesitate and just write me an email or maybe contact me just after the presentations. So thank you very much.
Okay, thank you very much. We of course have time for questions now, so please, we're open for questions. So maybe I will start with one question, because I'm not that familiar with this project. I mean, I'm kind of familiar, but you didn't mention several things. I mean, one of the things that are interesting to me is the counting of the user. I mean, it seems like when you're accessing or using the infrastructure like NMRs or radio telescopes or whatever, or you can imagine some other infrastructures, maybe more commercial based, you would be interested in getting the accounting information. So there are people involved who you probably have to pay for, and also the equipment, the network, etc. Do you have the accounting integrated with this solution?
Yes, of course. Because as you mentioned, when we are talking about providing users access to scientific equipment, there's of course the aspect of costs. That's the equipment costs lots of money. So we have basically developed our own accounting module, which collects this information. It was shown on one of the or two slides. I just go back. Oh, for example, here, that one of the steps that Global Scheduler, it's a module responsible for globally directing the tasks to Grid Gateway, checks with that module whether the user has enough credit. So we of course, the accounting is, we can account the task on various levels. For example, the user can schedule the task on one machine, but depending on type of task, we can count it for more credit than the other types of tasks. So we have a module which is responsible just for collecting accounting information and for displaying graphs, statistical analysis, and so on.
Okay, so are you able also to put the accounting for accessing the resources, but also like people's work that help you with the device, or it's not included in there? So I think it will be pretty interesting.
I'm sorry.
Like, accounting not only the user jobs, but also the person who works on the other side to put the probes, into the device or whatever.
No, not at the moment, because actually right now we are counting the time the user logs on to his application.
Yeah,
but
I understand.
Sometimes it can be understood as the time needed for the whole experiment. I mean, for the person on the other side also to perform his or her preparations, which are needed to perform the task.
I still have one more question.
Sure.
So VNC, talking about VNC, you've added some security mechanisms to VNC, right?
Yes.
So what are these? Basically, what are the mechanisms that you've extended VNC with?
First of all, we decided to use a secure connection. So we use the SSL protocol to encrypt the VNC connection, which in open source standard it's not encrypted by default. And another thing is that the VNC Manager application, which is responsible for running the task, the interactive application, it's a wrapper which actually starts the VNC server just before the task is about to be run. So the server is started, then the task itself, then there is a dynamically generated password for just this one session, and the password is transferred to the portal, which is encrypted and available only for the user which submitted the task. And after the user or the system sends a signal to end an experiment, the VNC session is terminated, the application is closed, the VNC server is closed, and the password is no longer valid. So we put a lot of effort to make it as much secure as we could, basically.
Okay, thank you. Any other questions? Last chance. Yes, go ahead. Just a moment, because we need to record all the questions, so you're going to get a mic. Okay.
Do your scheduling algorithm take into account some cost requirements of application? Because I can assume that interactive application might have quite strict requirements for latency, for loss, and so on and so on.
Well, basically we are relying on a VNC protocol. I don't know if you're familiar with the general concept of the VNC. And of course there are aspects of latency, but we restrict the use of this application, maybe not for the real-time process control. There are just the computations using software which enables to analyze some graphical data. It's not about the actual real-time process control, more about the analyzing data or maybe performing the experiments in a way that is not dependent on the latency problems. And of course, when we are dealing with broadband networks, with internet, is of course an issue. But unfortunately, we have some requirements which are also about the required network bandwidth to be able to work with our solution, with our system.
So currently, you assume that you have some ideal network?
Maybe not ideal, but it must be of some level that just to be accepted. It cannot be a slow modem connection, of course, but nowadays we are talking more and more about broadband connections, and everything above 500 kilobits per second would be okay for us, for our point of view, practical point of view.
Thank you.
One more question or two? Yes, go ahead, please. Could you please pass the microphone?
Well, I would really like to know how do you assign a cost and the price to user operation? What algorithm do you use? What type of metrics do you collect from the user tasks to assign a cost to the user jobs?
Oh, well, basically we compute cost. This is, of course, definable according to a given application, to a given device, for example, and the device owner decides what algorithm should be used. So far, it's more about charging for the time spent on the given device, not charging for the specific operations which are performed. They may be charged in addition to this accounting module, but basically we are charging for this amount of time we want to use the device for.
And what about prices? Who set the prices of the...
The prices are set by the device owner, and the prices are negotiable with the end users. Of course, we have created a system of laboratories, we call it, which are the groups of users, end users, which want to perform experiments of the devices, and the device operators set their fees. They can be negotiated with each group individually. So the fees are just assigned to the groups of people working in our system. So it's all up to the owner, device on the actual device owner.
Okay, thank you.
Okay, we still have time, so go ahead.
So you have implemented a workflow mechanism on the client side, and right now submit step-by-step tasks to GRMS. Are you interested in a new workflow mechanism coming from a new version of GRMS 2 something? Do you have such use cases in which you can define in advance a workflow experiment and send the whole workflow to GRMS, so then GRMS is responsible for the workflow, for the whole workflow, and informs users about the status of all these tasks?
Well, basically, we are aware of that solution, but it's a little bit more complex in our case, because maybe I'll just show you the slide with our dynamic application. It's not very easy to predict which task will be run, because there's a very non-deterministic process of obtaining the results. Of course, there are mechanisms in GRMS, but basically we put that work on our scenario management module, and it really does all that work. Basically, we put a lot of effort in it just to predict what are the possible paths that can be actually executed in our scenario management diagrams. Of course, we could implement that solution, but we are not considering it suitable at the moment. Of course, we can discuss it maybe later, and just maybe you can convince us to use that, but at the moment we have our very own specific solution.
I'm trying to convince you right now. In a case if you have many batch applications, and you have and in advance relationships between all these tasks, so you don't have to step by step send tasks to GRMS, because it takes time. You just if you know that some tasks are related somehow in advance, you just specify the whole workflow and send the whole workflow to GRMS, and you don't care about all these steps in the middle.
Yes, that's correct, but you're saying mostly about the batch jobs, which are run in the background and without the user interactive part. So maybe right now we are dealing all the tasks in the similar way. We are just put it in the diagram and just send it independently. Maybe we could apply the solution, but with the restriction that it could only be used in case of a batch jobs. But we have that mix of batch and interactive ones. So basically right now we are treating them mostly in the same way. So maybe we can discuss it.
Okay, yeah, I think we should put this discussion offline maybe. Okay, thank you again very much.
Thank you very much.
Okay, our next speaker is Michał Kosiedowski from PSNC, from the Applications Services Department, Network Services Department. And Michał will present his work, his team's work on the access to computational resources using the Progress project tools and services. Okay, the floor is yours.
Well, thank you very much. My talk will be at a bit higher level than the two previous talks, especially at more high level than Krzysztof's talk. I'll be rather talking about such distributed applications that would take some input information, run this, analyze this on all sorts of services distributed across a network, and turn it into a resulting information useful for the user. So such complex distributed applications that I'm talking about would use all those sorts of distributed systems. I will show you some of those in a second, and would use those distributed systems in some complex scenarios. And to be able to efficiently and flexibly realize such a distributed scenario, we really need a model for an access environment to such distributed applications so that those scenarios can be realized in a flexible and efficient way. And so we have such a model. We have designed this, and we have already used this to some extent in some environments. Okay, such distributed systems that I'm talking about one of these is a computing grid, such as Krzysztof was talking about, which was done, for example, by the GridLab project here. The other distributed system I'm thinking about is a grid data management system, like the one we have developed within the Progress project. Another one is a distributed digital library, like one which would connect all those Delibra instances that are currently being installed across the Pioneer network into one huge distributed digital library. And another one is a content delivery system, like the one which is the basis to realize interactive television services within the ITVP project. And you could add many more to this list, like e-learning or any commercial systems which use some distributed resources, which provide some distributed services. Okay, and those distributed systems can be used in some complex distributed scenarios, and I will show you 3 of them. Let's, for example, assume that we have some hospital with some doctors, and the patient comes to this hospital with a completely strange illness, and the doctors don't really know what to do with this. The only thing they know is a virus, and they can get some parts of the virus DNA. And what they can do now is they could digitalize this and send to a computing grid to get the whole DNA sequence of the virus. And this DNA sequence could be then compared in a grid data management system to find to some known ones residing in some gene banks, DNA banks, to get possibly the virus name, or at least the type of the virus. And this information could be used to retrieve some information like publications about the virus in a digital library. And thanks to this, the doctors possibly could cure the patient. In another scenario, another medical one, we could have some serious accident leading to some serious injury. And again, those doctors in a local hospital in the middle of nowhere don't really know how to proceed with this injury to best cure the patient. But what they can do is they could get a Röntgen picture and again send this to a grid data management system with some data bank to compare to the known cases from the past and possibly get some injury type. This information together with some other health parameters could be used to retrieve some information, to retrieve some reference cases from a digital library, which could help the doctors to cure the patient, to give them some directions. And such a reference case could have also some references to some instructions, some video instructions, which a content delivery system could deliver to the most convenient place for the users, for the end users, for the doctors to view the instructions on how to perform the operation that is required, is necessary to cure the patient. And so together with these instructions, together with the other information from the reference case description, could lead to an appropriate treatment of the user. Okay, these were two scenarios with some less optimistic start, but we could also have a bit more optimistic one. Like most of us will probably have some holiday soon. The summer is coming, so I wonder if everybody knows what to do with his or her holiday. But we all certainly have some travel preferences. And these travel preferences could be sent to some travel reservation system, which would, based on those, would book the hotels, would book the plane tickets, would book a car at the rental service, would, I know, reserve anything else you want, and would come up with some options, some already booked options and travel destinations. These could, again, be used to retrieve some additional information about those proposed, those suggestions prepared by the travel reservation system. This could be used in a digital library to find this information. And again, we could use a content delivery system to get the documentary video close to the user, to the most convenient way, location, so that the user could see this, could analyze all this information, and possibly decide which of the travel options is best for him, and decide on the vacation he will spend this summer. Okay, and it will be really nice to have such such complex applications which would use all those distributed systems down there. But what is also important is that it must be really easy to use those applications, and it must be really easy to use those applications from many different locations, like from many different portals. And so what we could do to enable such distributed applications within portals, we could simply create the appropriate workflows within portals. Simply hard code this into a portal. Sure, this would work, but this would lack flexibility. It would be really hard to reuse these applications in another location than the original one. You could say that we could take the portlets, because we would most probably implement this as a portlet and redeploy this portlet into another portal. But what if this portlet and this application requires some additional systems, some additional tools, like, for example, a relational database, which I, as my new portal operator, I don't really have and don't want to install it. Okay, but we have this nice WSRP standard to access remote portlets, and this would really work. And let's even assume that the network is so good that the network traffic between Australia, USA, and Poland wouldn't be that bad. Probably it wouldn't be with today's networks. But anyway, the load of the original of this Australian portal would finally grow to the level that eventually this Australian portal administrator would cut our access to this portal, and so would be left with nothing. So what we actually should do is we should put some high-level services to manage such complex applications. So that's what we propose, to introduce an additional layer of high-level services which would be grouped within the special modules called service providers, and which would manage abstractive descriptors for such objects as starting with computing jobs, computing applications, going through medical reference cases, travel destinations up to complex distributed applications. And these services would manage those objects, would store them in an underlying database. This is the place where a database is highly recommended. And those services would utilize the functionality of all those distributed systems that I've been talking about previously, and that would underlie below these service providers. And to be able more efficiently realize those specific tasks sent to a computing grid, to a digital library, to a content delivery system, it would be very beneficial to have a special brokerage service on top of those functional systems. And such broker services are already available. ISAM, Krzysztof was talking about one of them for a computing grid, GRMS. We have the same sort of service in our data management system, which is, by the way, used by the VLab project. And those broker services simply accept tasks coming from the upper layers, right? Like would accept tasks from the service providers. Okay, how does it really look like? So we have all those distributed systems like a computing grid, data management system, digital library, content delivery system, and we have the broker services on top of those systems which allow to easily access their functionality. And then we have all sorts of high-level services grouped within service providers, like a grid service provider for computing, telemedicine, digital library, ITVP, interactive television service provider. And those services can be accessed from multiple portals deployed across the network. And the portals here are only for the interaction with the user and for the presentation of the data coming from download. They do not really analyze anything that any information or they do not perform any tasks here. What is also important, just as a side note, a service could use as another service at the same layer to realize some task. Like, for example, a good resource broker like a GRMS would use a data broker from the data management system to store the results of a computing job. Okay, and this was what we proposed. This is an architecture that we designed, and we actually have used this one to some extent. The first attempt to implement our architecture was the Progress grid computing portal environment, where we have a grid service provider featuring two services, a job submission service and an application service, management service. And those services can be accessed from multiple portals. And in fact, we have also, in a real production environment, we have the most widely accessed service is an additional service for more testing purposes that we have developed, which is a new service and which is used from several different sites and accessed from several different sites. And so those services may be accessed by multiple portals, and to facilitate the constructions of those portals and the construction of specialized user interfaces such as portlets, we created the Progress portlet framework, which allows to really quickly create a new portlet. And the Progress HPC portal is deployed in the Pioneer network. We have some computing and data storage resources across the country connected by Pioneer. Okay, and another implementation of of our architecture is the one that is currently under development. This is about telemedicine, and it's about a solution for surgeons. And the telemedicine service provider, which we currently implement, will provide two services: a teleconsultation service, which will help the doctors in local hospitals to get the expertise, to use the expertise of the clinic experts from a clinical hospital here in Poznan. And also the other service would be the reference cases service, which would manage, store, and enable some reference cases and for the use of the doctors, so that they can learn, or they can use those information to cure the patients at a regular daily basis. And again, this is also in the Pioneer network, this time at the regional level. We are using, we want to utilize the Pioneer network links that are going through Wielkopolska region here around Poznan. And what we want to do is we want to connect those local hospitals in small towns like Grodzisk, Chodzież, Kalisz, which are here around Poznan. And we want to connect those hospitals with clinical hospitals here in Poznan. We simply want to deliver the grid resources and services to local hospital through the optical network. All right, this was quick again, I guess. And to summarize, we introduce another layer in between portals and the distributed, all sorts of distributed systems, like a computing grid, like a data management system, like a distributed digital library. A new layer group, which is called the service providers, which group high-level services, and this and the introduction of those services adds much flexibility to the construction and utilization of distributed applications of the type that I've been talking about today. And the possible realization of such complex distributed scenarios as the virus, as the injury, or as the vacation scenario I presented 15 minutes ago is much more easier to achieve. We're simply going into that direction with our architecture and our projects. We simply want to use this architecture for the realization of some grid service environments, and we want to use this architecture to deliver some complex distributed applications in the Pioneer network. And the model was in fact used already to deliver a computing portal environment by the Progress project, and is currently the basis for the realization of the telemedical solution. And we also plan other environments, like a portal for small and medium enterprises, where the users, all these distributed applications are for those users that are not really advanced, that are not scientists, maybe that are not that are not computer scientists like us, and that really require an easy and flexible access to the applications. Thank you very much.
Thank you very much. Questions? No questions? I also don't have questions. Okay, so
just our presentations were so
so clear. Yes, right.
You know.
Okay, so thank you very much again. Thank you all the speakers, and thank you all the audience for coming here and listening about PSNC's projects and achievements. Thank you very much.